like where we are. So, if you go to a town, you often find this kind of map, you are here, and you look around. So these days, of course, you go to Google Maps, okay, we are at the Institute for Advanced Study, we are here in Princeton, but what happens if you kind of zoom out? So where we are. So if you would have a Google Maps of the universe, you would have something like this. So we are planet Earth, we are in the solar system, we are in the Milky Way, in the galaxy, we are in the universe. So I think what we are doing today is just getting a feeling where we are and getting a sense of the distances and sizes. And in some sense, it's kind of an interesting story because, humans always felt that they were the most important in the whole world. And in fact, if you go back not that long ago, then you would think of the universe as something where the Earth would be right in the middle. So in some sense, we would be right in the center of the whole universe. Everything would be rotating around us. You see all these maps. You have the Earth, and then you have the planets and the stars, and all rotating about us. So basically, it would tell us that we are the most important thing in the universe. So perhaps that's true for each of us. But what's the idea of science about this? And another question is now, how long have we been around? So not that long ago, people thought they know exactly when the world was created. Does somebody know how old people thought that the world was? For many, many, many years. Does somebody know this? They knew actually the exact day. Do you know? 1,000. 1,000? A little bit more? Yes. Yeah, in the back? Yeah, very good. In fact, they thought the world was created in the year 4004 BC, and in fact, they knew it was on October 23rd. And there was a lot of debate, was it in the morning or in the afternoon? In fact, there was a famous archbishop who calculated using the Old Testament, where you can see how many years people lived, exactly the moment of creation. And but he actually couldn't figure out what the precise hour was. And then one of his colleagues calculated it was 9 o'clock in the morning. So this was the number. Now I think that it's not quite a number. No, the world is a little bit older than 6,000 years, and we actually learned about this. And of course, all this changed when people start to not only think about it, but actually measure. Using telescopes. The first telescope was used in 1609. Galileo, you all perhaps know the story. There was a telescope was used during the daytime to spy, to see ships, etc. And he was the first one to realize, wait a moment, when it's dark, I can't see ships, but I can look up into the sky. So he was the first one looking into the sky only 400 years ago. And then, we got a very different idea of what the solar system is. We have figured out that actually the Earth is rotating around the sun, and it's like this beautiful clockwork you can see here. And we all learned about this. But I think it's one thing to learn about the planets, another to realize exactly what the distances are. So I have a few ingredients. So we start to make a little miniature solar system just to figure out how that works. So I have to start with the sun. So usually I have this orange, be the sun. So you want to be the sun? Okay, you hold it. So then we have to figure out what the Earth is, and actually the Earth is this peppercorn. You see it here? So the question is now, where should the peppercorn be? How far away? So let me just put it where it should be. It should be here. So you will be the Earth. Here. Okay. So that's a long distance, and one way to compute that distance is to measure how long light takes to go from the sun here to the Earth. And in fact, it takes 8 minutes and 23 seconds. And that's pretty amazing, because if you think of a light going from the sun to the Earth, it goes really slow. It goes like a turtle or something. It will take an hour to go to the end of the dining hall. So it goes really slow. And if you would, I would also like to put the moon, but the moon would be just a little grain of salt, and it would be 1 inch away from your peppercorn. So you see there's a lot of empty space, and So who knows what is the biggest planet in the solar system? Jupiter. Okay, so you can be Jupiter. So I have this blueberry here. So where do you feel you should go? Yes. More or less. I think you should go actually to the other room. No, you can stay here. But it's roughly 50 meters. And if you want to know how big the whole solar system is, it's like 1 kilometer. So it will be going to town, basically. So that would be the solar system. And so now the question is, if you want to, please come back, because that actually, if you want to go to the nearest star, does somebody know what the name is of the nearest star, by accident? Proxima Centauri. So actually it's roughly like this cherry tomato. So where you feel you should go?
Princeton downtown.
Can somebody top that?
Massachusetts.
Can somebody top that? It's roughly 2,000 miles, or 3,000 kilometers. You would go to Mexico City. So that's the next star. So actually that gives a feeling of the huge distances in the solar system. And I think the first conclusion is how much empty space is there, right? And how long it takes. So for instance, going to Mexico City will take you almost 4 years with the speed of light. So if you think of this system, then light is going very small. So we think about light going extremely fast. But on the systems of the universe, it's actually going pretty slow. So it will be difficult to go beyond the stars. So one thing that we can now do, we have computer animations that show you the positions of all the stars as they really are measured. So here we go. So this is a fly through the universe. And all these little pieces of dust are actually stars. So think about, it takes you, they're typically 4 or 5 light years apart. So already here we are 10, 15 light years away. So we're going here through the, so one of these piece of dust is the sun. Good luck finding it back. So this is the Orion Nebula. This one some of you might also know. Look closely. That's the Horsehead Nebula. So these are big clouds of dust in which stars are born. And literally, this is not just a visualization. All these little dots are actually measured positions of stars. That's the Rosetta Nebula. You see, it's very dense clouds. A lot of young stars are born. And in fact, this is also very interesting. You see this nebula coming here. That's the Crab Nebula. And that's not a place where stars are born. This is a place where a star died. And he exploded. And in fact, there is a neutron star in the middle. So that's why we're not flying through, because that would be kind of very dangerous. But you see, now we're zooming out. And I think this is really beautiful, because you see that we are in the galaxy. And the galaxy is this huge cloud of stars. And slowly it comes in. And if you would go back 100 years, this is roughly what people would think the universe was. The universe was this big galaxy. Now you could see it on the sky. And even thinking about the galaxies is really very complicated. For instance, how long would light take from one end to the other? It would take like 100,000 years. And so somebody has an idea how many stars are there in the galaxy? Who tries to make a guess? You. 1,000? 1,000? I think it's more. You? No, that's too much. You. 1 billion's close. 6 billion? A little bit more? Yes, you? 8.5. It's roughly 100 billion. And just to think about 1 billion, so my favorite way to think about 1 billion, so I have this bucket of sand here. It's very thin sand, so very small. And this is roughly 1 billion. So if you want to think about 1 billion, you should have a big bucket of sand. Everybody should have a bucket of sand, just to remember what 1 billion is. So I would have 100 of these buckets, just to think about the galaxy. And actually, in some sense, it's again like the solar system. So the star, our sun is one of these stars. Though this is, of course, not the galaxy itself. It's not a galaxy, but it's roughly at 2/3 here. It's like a small provincial town. It's not even a capital. And it's orbiting around. So there's like the year in a galaxy takes a long time. In fact, it takes 220 million years. So the sun has been going around 20 times since it was born. So it's like 20 years old in galaxy terms, in terms of the Milky Way. And, but of course, this is not the end. So I can kind of go on. And since 100 years, roughly, we know that it's not just the Milky Way that's out there, but it's much more. So let's continue the movie. So here we're zooming out. We're seeing the Milky Way. And you see that it's not an empty space. There are little kind of dots around it. Little clouds. And if you look closely, you see actually that these clouds, all these clouds themselves are again galaxies. In fact, if you move out, now we are roughly 2 million light years away. We see two of these galaxies, which are very close. One is called the Triangulum Galaxy, that's this one. And this is the Andromeda Nebula. And in a few billion years, they actually will collide with the Milky Way. They will make one big galaxy. So these are our neighbors. But if you zoom out more, you see actually that the whole sky is filled with galaxies. And these galaxies are not just randomly distributed. If you look closely, they're like kind of filaments. So they're like clustered together. And you see that actually we are not the center, because if you look closely, you see already here, this is something where a lot of action is happening. So this is what we call the Virgo cluster. It's a place where many galaxies are sitting together. So if anybody has a claim to be kind of a capital or a metropolis inside the universe, it's actually that location. And so even our galaxy is not, our Milky Way is not very special. And so here the movie zooms in, it's beautiful, and zooms in this very big, we call it elliptical galaxy in the middle. Now there we go. This huge thing here, see it's really a big fat galaxy. It's roughly 200 times more stars than our Milky Way. And the movie stops because we kind of end right in the middle of the galaxy in this huge black hole that sucked up the documentary maker that actually made this galaxy. So now we have a much better understanding of the universe. We know it's not only 100 billion stars in our galaxy, but 100 billion galaxies in the part of the universe that we can see. And so an important question also is, well, if there's all that stuff around, for how long was that here? And I think that, how old is the universe, that's the question that we've answered. And does anybody know the precise age of the universe? Because I think you should know the age of your universe that you're living in. So we're trying to get.
13 billion years.
Almost 13.
17.5.
No, it's 13, it's actually 13 point something. Yeah, 13.8, that's right. 13.75 something. So one way to illustrate this is think about that you have a book, and every page of the book takes 1 million years to read. So then, and each book has 1,000 pages. So here I have 14 books. It's the encyclopedia, which describes the history of the universe. And so this is the first book. Now if you open it up, you find the very beginning. We will get to the beginning. But of course we are now living in the end. Now we are here in the last volume. So it takes 1 million years to read every page. It takes 1 billion years to read a book. And so we have 14 volumes. And so it's kind of interesting to see. So for instance, the Earth was created roughly here, and volume 10. And quite soon after that, life was formed on Earth. So life on Earth is these last 4 volumes here. And it starts with what were the first kind of living things on Earth? Who knows what the first living things are? Yeah, single cells, like bacteria or something. So the first volume here, that's number 11, is bacteria. Then the next one is bacteria. Then the next one is bacteria. Then the last one is bacteria, roughly for the first half. So halfway, volume 14, on page roughly 500, the first kind of really animals and plants appear. And so these are not, of course, dinosaurs or something, but more like, what kind of were the first kind of animals? Yes? Sponges, somebody else? Yes? Trilobites, yes, exactly. So kind of things which look like horseshoe crabs or something like. So, and does somebody know, like if this is the last volume, when did kind of something which looked like a human appeared? On which page? Any idea? Yes? The last few pages, exactly. In fact, the last 3 pages. So the last 3 pages are about us, but of course, no, not really, because we were kind of... last 2 pages, yes. And in fact, if you think about the modern human being, so somebody who would look like us, think like us, where do you think that that person would appear? It's basically the last paragraph here. It's the last paragraph. And then if you think about learning about history, like you learn about the Babylonians and the Egyptians, that's actually the last word here, but it happens to be town, which is a good word. And us, it's like the period here. So the period here, so that's us, which is pretty amazing, in fact. So we have this whole 14 billion years, and of course we have to read about it and we have to learn about it. But the question is now, why do we know this? How do we know it's 14 billion years? And now, of course, this goes down to a person who's rather famous. Somebody recognizes this image? Who's this? Who's this? Yes? Albert Einstein. Albert Einstein, of course, is very famous, but particularly, we like him very much here because he was actually at the Institute for Advanced Study for the longest period in his life. So he was in many places, but he lived here for 22 years, and so he's very dear to us. But Einstein did many things, but I think he really put to work to understanding the universe. And he had many ideas, but so one thing he had is he really thought differently about space and time. And so that is kind of difficult because, okay, so if you think about space and time, so you know what this is? Somebody recognize this? It's a very old-fashioned thing. What is this? Yes? A film, yeah, it's a film roll, a movie roll. So you see all these pictures here, it's very difficult to see. But in some sense you can think of this as every picture is just a picture made in time, and this is early in time and it's later in time. And one thing that Einstein, it's kind of perhaps a bit complicated to explain here, but I'll show it anyhow. So here you have a simple movie. And what Einstein basically said, well, you have to look at all these different movies and stills and basically think it as one big thing. So he said, let's cut out all the little pictures in the movie. Like you have a whole pile of pictures. And you can think of it as something, that time is going, this is space and this is time. Time is going upward. And he basically said, let's look at the whole thing. Let's look at space and time together. So in some sense he said, let's understand the universe not picture by picture, but let's understand the whole thing, which is very difficult for us as human beings, right? Because I can't look at the picture like this. I have to see it screen by screen by screen. And not only he could do that, he did something very, very crazy, which is very difficult to explain. But he figured out that space, people actually always thought that space was made like of something very tough, like this stage here, something that you can stand on. Now, space is something we can live in, but Einstein actually found something very crazy, totally crazy. He found if you put something in space, that actually space reacts. Space kind of starts to curve. It's like it's made out of rubber instead of something very solid. And so once you put something in space, the space itself changes. The shape of the space changes. It's very difficult to see. Very difficult to see. But if you kind of move in space, then you would be kind of, you can't go straight. You will kind of have a curved space. And so if you try to go straight, you would actually be curved around. It's like if you riding your bike, in the hills. You will go like this and this and this and that. And Einstein then said, I have actually a wonderful prediction I can make. I can actually, if you have a ray of light, and it would travel through space, and it would travel very close to the sun, so hold up the sun here. So there's the sun. And the light would go, it would go very close to the sun, it would actually feel the force of gravity and it would deflect. It would slightly change its course. And he also said, I know exactly how to measure this. You have to look at the stars very close to the sun. Now, did any of you ever see stars very close to the sun? And if not, why not? Can you see stars very close to the sun? Yes?
No,
Why not?
because there are no stars near it.
There are no stars?
Near the sun.
No, but I'm just thinking, you look at the stars in the sky, you look up to the sky, and you want to see the stars just behind the sun. Yes? The sun is so bright, so you can't see them. So how can you make sure that the sun is no longer bright? How can you make sure that the sun isn't shining? Can you switch it off? Can you switch it off? Yeah?
No, because the moon comes up at night by itself.
Uh-huh. It all goes, nobody can switch something off, right? No, they go to the... So, but is there once a time in the year, perhaps, is there a moment where you look at the sun and suddenly the sun gets switched off? Yeah? A solar eclipse. And so Einstein made this discovery in 1915, which is, next year will be 100 years. And he had to wait for the next solar eclipse. And actually the solar eclipse was in 1919. And so there was an exhibition going, an expedition going there by the famous British astronomer Sir Arthur Eddington, who actually did this experiment. And the wonderful thing I didn't bring, I should brought it, that here in our archive, we have one of the original pictures made by that expedition, which you see here. This is the sun, and the moon is in front of the sun, so it's a solar eclipse. And by measure very carefully the stars here, close to it, you can actually measure the effect. And so at that moment, something really dramatically happened. Einstein had this wonderful discovery about the universe, and he became instantaneously world famous. Now he became perhaps the most famous person in the world. And in fact, he traveled also to the US, and it was great. So here I have here is a little piece about him traveling to California. We don't have images of him arriving in Princeton, but this is the next best. And there were lots of children. That's a good warm welcome.
Professor and Mrs. Einstein, it is my pleasure to welcome you to the city of San Diego and to the state of California.
So he says, thank you for the warm welcome, and in particular, it was a great delight to see the young people, the Vrouwenjugend, the young youth present and singing to him. And I think that's one thing that all the stories here in Princeton is about how Einstein liked children, and so he really became world famous. But he not only became world famous, he was the first person in the history of the universe, perhaps, but certainly in the history of the Earth, who could actually make a computation about the universe. So he had his theory, and he could compute what would happen with the universe. And he found something spectacular. He found that if you take the universe and you just look what happens with his theory, the equations, it starts to expand. It grows. And he also knew, well, if it's growing in the future, then in the past, someone had to start at a moment. So he figured there should have been something like the Big Bang. And that the universe would have started some time ago. That was such a silly idea, so crazy, that he actually did something very, very stupid. He changed his theory. He modified the theory, he put an extra term, which we now call the cosmological constant, so that the universe could keep on living forever. And afterwards, and now we know that there was a Big Bang, otherwise you wouldn't have come. You would come to a lecture about the Big Bang if you feel this is kind of a silly thing. So now we know, and when people told him, well, Einstein, you were right, there was a Big Bang, he said, this was the biggest blunder I ever made, Because he should have predicted that the universe started with a Big Bang, but he didn't dare to. In fact, the way we found out that the universe was expanding was through observations. And the great American astronomer Edwin Hubble actually made very close observations of the universe. And he was the one who figured out that these little clouds in the sky were not little clouds, they were galaxies themselves. They were galaxies, they were far, far removed from billions and millions and sometimes billions of light years away. And so he actually figured out how big the universe is and also that the universe is expanding. And he did this by using a very famous scientific effect that I introduce now using perhaps the most famous physicist at this moment in America. And in fact, he's so famous that his kind of university he works is called Big Bang. So here he is.
Hey, Sheldon, there's something I want to talk to you about before we go to the park.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. The most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and Peter Pan. That's so cute.
Actually, Penny, he's wrong.
Not Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. I hate what Sheldon's
Now
supposed to
pay attention.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay. So that's the Doppler effect. And the Doppler effect is actually something you all know. And I'll just demonstrate this with a little movie about a car. But in fact, it's the way in which we figured out how big the universe is. So it's very important to realize. So this car will zoom by, and so the question is what will happen. And let me just listen to it, and you will recognize the effect. You hear it, right? If a car is coming towards you, the sound is, how would you describe it? Yes. What happens if? Huh?
It's at first it's quiet and it gets louder and louder and louder and louder and louder.
It gets louder, but there's something else. Is it just what happens? If you listen to the pitch,
The sound kind of changes.
it changes, yes. And if you listen carefully, perhaps we should listen again. It's a high pitch when it's coming towards you, and it's a low pitch if it's going away. And the same is true for light. So if you look at there it again. Listen. It's going down, in pitch. And in fact, the same thing happens to light. So if you have a star that shines light, say it's kind of a yellow star, if the star is moving away from you very fast, it will be red. It's the same thing, it's the kind of light basically being a low-pitch light. And if it's coming towards you, it's blue. And Hubble, he measured the light of all the galaxies. And he found actually that if galaxies are far away, they're also moving away from us very fast. And these days you can make that very careful measurement. This is a map of the sky of all the galaxies we see. And you see that they have all kind of different colors. Some galaxies are moving away from us, and others are not. And so how should you think about it? And now here again, there's my own little version of the experiment. So this is the way to explain this. So this is my universe. So here it is. So these little stickers here are the galaxies. And so what's happening, basically, as Einstein found, and what the astronomers found, if I blow this up, oops. We have a Big Bang here. But this demonstrates something important. You see that the size of the galaxies is not changing. Now, it's not that the universe is expanding, that you are expanding, that you become larger and larger. It's not that our solar system becomes larger. It's not true that our galaxy becomes larger. It's in fact not even true that our local group of galaxies becomes larger. It's the interstellar space, it's the space between the galaxies that increases and increases. At a very slow rate, if you would grow as fast as the universe, you would grow a few atoms a year. So it's very slow. But of course it had 13.8 billion years to grow. And that's why it's now so big. So if the galaxies are expanding, if the universe is expanding, is there some way? So then you have to figure out that at some point the universe was very small. And we find out in a moment how small it was. In fact, I can already tell you. How small do you think that our part of the universe was, when it was really, really, really young? Who dares to try? You know how small it was? It was this small. It's pretty amazing. But now if you take the Big Bang Theory serious, and we do, I'll tell you in a moment why, the whole universe that we can see now with these 100 billion galaxies, each filled with 100 billion stars, was roughly the size of this little ball. So that's pretty spectacular. You have a question? When it's yes, so the galaxies grow, of course, that's true. Now, I mean, they weren't kind of tiny galaxies inside here. We'll see in a moment what happens. But because at the moment when the universe was this little ball, there were no stars, there were no galaxies, there were no planets, there was something else. So we see in a moment what is there. But the question is now, how do we know there was a Big Bang? How do we know? This is kind of a silly idea. It's just a story. And the first person actually to think that maybe you could still see or better hear the Big Bang was a famous Belgian cosmologist, Georges Lemaitre. He's kind of famous because he was also a priest. And here's with Einstein. Actually, that was one of his visits to Princeton. And here's with the Pope, so he was well connected. And he was the first person to realize if the universe started with a Big Bang, you could still kind of hear somehow the sound of the Big Bang there. But this was not really taken very seriously until in 1964, exactly 50 years ago, quite close by again. So New Jersey plays an important role. So in some sense, we might be the center of the universe. In Holdell, New Jersey, where there was a lab, the Bell Labs, and there was this telescope here, which was more used for communications with satellites. It was a microwave satellite. And there were these two engineers, and they were quite young. In fact, this is the picture taken when they got their Nobel Prize 10 years later, but at that time, in 64, they were very young. And they were asked to solve a problem because there was a little noise in the detector. And in fact, let's listen to the noise. So they wanted to use this for, for radio, etc. But this is kind of annoying, isn't this? You would like to kind of tune it down. And so they tried to remove it. So they said, oh, let's look at the circuitry, let's look at the thing. In fact, there was a whole nest of pigeons in it. So there was a lot of pigeon material in there. They removed it, and they kept working, but they couldn't get away with the hiss. It kept. And at some point, they discussed this with some astrophysicists, cosmologists here at Princeton University. And they said, wait a moment. You are doing exactly what we plan to do. We want to build a telescope to measure the sound from the Big Bang. You already found it. And they did. So what you just were listening to is actually the sound of the Big Bang. Of course, it's after 13.8 billion years. So it doesn't sound like a Big Bang anymore. It's going to quiet it down. And in fact, you can also see it. If you take your television set and you unplug it, now you get this static noise, the little pixels there. 1% of these pixels is coming from the universe. So I always find this a wonderful feeling. Now you look at this screen, and there is a light particle that was emitted at the Big Bang. It traveled for 13.8 billion years through all these pages. You know. And think about how long that was, because it means like you take 1 grain of sand, you know, every year, and you have to work through 14 of these buckets of sand. That's a long time. And so this signal was traveling all the way till it hits your television screen and makes a little dot. So we can actually measure this. The sound of the Big Bang is still around us. And we can measure it much more carefully. And now we have satellites. So this is a famous satellite that went up in the 1989. And it looked at the sky and looked at the signal and it said, wait a moment, I can look at various parts of the sky. And they noticed that the sky isn't the same if you pick up that signal from the Big Bang. There are some pieces where it's a little bit more intense than in others. So you get this beautiful map here. And when one of the discoverers was asked, what do you see? He said, this is the fingerprint of the creation. I think it's like a baby picture of the universe. And in fact, it's not really the Big Bang. It's a picture when the universe was 380,000 years old. So it's not, so you want to say, okay, so this is volume 1 of the universe. So we're going to volume 1, page 1. And I want to know, of course, what's here, the first letter. I can't. But I can halfway the page. We can make measurements. So we are now here, halfway the first page. And we can see, literally with our instruments, what was happening there. And we have these beautiful pictures. In fact, this is the famous WMAP satellite. It's a wonderful program initiated by Dave Wilkinson, a professor. Fortunately, he's no longer with us at Princeton University. So we at Princeton are very proud of this map satellite. So this is the picture they made. It's even more beautiful. It looked like an abstract painting. And just this year, the results came from an even better satellite, the European project, and you see it's even more detailed. So we can actually not only hear the Big Bang, we can see it, and we can kind of see how the universe looked like. Halfway the first page of the first volume of the 14-volume set, History of the Universe, that's here in front of us. So what do we learn about this? Well, one thing you should realize that this map here, it's the map of the sky. So you should think of it the same way if you, for instance, look at the map of the Earth. You know, it's actually the Earth is a round, is a sphere. The same way the universe is a sphere. And you can think of this is as far as we can see. Now, if you take telescopes, you can see galaxies. You can see galaxies that are even further away. But you can look at almost at the beginning of time. So you think of us, here's the Earth in the middle. Here are galaxies. These are very distant galaxies. And these little dots that you see is just after the Big Bang, as far as you can go. And so if you could look at the sky using microwave eyes, the microwaves that you use to heat up a sandwich or a cup of tea, if you could have microwave eyes, you would see not little pigs. These are the things you would see, if you look with ordinary eyes. But with microwave eyes, if you would be kind of superhero, you would see something like this. You would see actually this pattern of dots on the sky. And you could almost see with your own eyes the result of the Big Bang. So that means that now we actually have reconstructed the whole history of the universe. So these 13.8 billion years, I can now summarize in less than half a minute in a little movie. So this movie is sped up. It's not going in real time. It will take a long time. But here you see what happened. Oh, sorry, I already clicked. So let's go to the beginning. Here it is. So what we do, we kind of zoom in. So here we have these little clouds. You see gravity makes sure that these clouds get attracted. They form dense clouds. Then the clouds kind of ignite. Stars appear. Very young stars. The stars, they combine. There's these big flashes, which are supernovas and quasars. Then, they combine into galaxies. Here you see all these galaxies. And one of these galaxies is actually ours, the Milky Way. And on the Milky Way, there's this little peppercorn. Is the peppercorn still there? Yes? Yes, the peppercorn is still there. And that's actually somehow the history of the universe. So we have reconstructed it. This is pretty spectacular, I would say. What I find most spectacular is that this whole history of the universe we constructed here on planet Earth in like 400 years. So it's like in the length of the last letter of the dot, the period at the very end of the last page. We constructed the whole thing. And we have this wonderful picture of how the universe evolved. So that's our history. We should learn about it. So are we finished? Well, we aren't. So let's just see exactly, and again, this is a movie, not an animation. It's a movie that shows everything of the universe that we know right now. So we start zooming in. So here is our sun. We zoom out. We get the local stars close to us. No, this is our local neighborhood in the Milky Way. That's the Milky Way. Here come our companion galaxies, Triangulum and Andromeda. We zoom out. These are real images of real galaxies that are really measured. You see, this is the local group of galaxies. We zoom out, more and more galaxies. Now, we haven't measured all galaxies. So you will see that the galaxies that we measured, they're like slices through the universe. There's like these butterfly wings, because our telescopes are only looking at certain regions of the... And now we zoom out. You see, and we zoom out, and then we get the outer sphere, which is the cosmic microwave background. That's the signal from the Big Bang. So this is the piece of the universe that we have mapped right now. It's pretty spectacular. Now, it's not everything, but we're a little bit like these old travelers, the explorers, who had a part of the world mapped out. And some part is not mapped out. So it's kind of terrific, but there's still some questions. So if you look at the galaxies in the universe, you see that they are all... So each dot is a Milky Way. So we have to remind us, and it's very easy to think about this as stars. Each is a Milky Way. Each dot has 100 billion, 100 of these buckets of stars. One of these grains of salt is us. Think about it. And there are 100 billion of these dots, but you see they're not like just all randomly distributed. They're kind of clustered together. So galaxies like to be close to each other. And why do they want to be close to each other? Well, because they are glued together. But what is the glue holding them together? This is a recent discovery. There is something in space. So here's our Milky Way. It turns out that the Milky Way is surrounded by a huge cloud, we call it a halo, of stuff. And the stuff, we don't know what it is. It's actually invisible. In fact, better to say it's transparent. Light can go through it. But there's a lot of stuff around the galaxy that we can measure indirectly, and we call it dark matter. So it turns out that our galaxy is surrounded by a huge cloud of kind of dust. And in fact, this is true for all the galaxies. So you can't see it, but here in using scientific methods, it's kind of colored blue. So we make something visible which is invisible. So suppose you would understand the dark matter, you could make a movie of the universe where you could see this dark matter. And this is done in this computer animation. So this is a computer animation, it's not real data. You see there that the galaxy, so each of these bright spots is a galaxy. You see there are these kind of strands of material going through, and big blue clouds. So here is one of the centers of the universe. And so there's all the blue stuff there. And in fact, there's much more of that dark matter than there is matter in stars and planets and clouds. And you see that's kind of it really holds the universe together. We have no idea what it is. So that's a big, big mystery. This is kind of a wonderful discovery we didn't think that we would find. But apparently there's much more stuff in the universe than we know. And there's another crazy thing. In fact, what happens is that we look at the expansion of the universe. So I say the universe is like a big balloon. So you blow it up. And it goes very slowly, right? Again, it goes with a few billionth of a percentage every year. So I just blow it up very, very slowly. But you can measure this. And what astronomers found is that it not only is expanding, but the rate of expansion is increasing ever so slightly. So it's like you're in a car and you push the gas and the accelerator, and it's speeding up. The universe is speeding up, so it's expanding. It's quite dramatic. And so that means in 100 billion years, all the other galaxies basically will be so far away we can't see them anymore, which is, we're just by ourselves. So it's kind of a distressing thought, I think. So we're just with the galaxy. And also, we don't know what this... And in fact, the crazy thing that in some sense, Einstein, when he changed his equations, and you should never do this, and he called this his biggest blunder. Now, Einstein was so smart that the biggest mistake he made was like genius. Was just absolutely wonderful, because now we notice that the thing that he did, he changed his equations in a way that actually nature is using. So in fact, this new force he thought of, we call it dark energy, it's out there in the galaxy, in the universe. And the universe is expanding, faster and faster and faster. And we don't know what it is, but apparently there's some mysterious force in empty space everywhere. So it's in between the galaxies that is pushing the universe apart. The universe wants to kind of fly apart. And this is, again, big mystery. We don't know what's happening. So if you think about it, if you think about the universe, we know that this is a famous picture. We know that roughly 5% of the universe is made out of stars, out of planets, out of us, out of the light. Anything you can study in school, at the university, here at the institute. And 95% of the universe is missing. We have no idea what it is. 27% is this dark matter that holds the galaxies together. 68% is a force that pushes the universe apart. So, on the one hand, I'm very proud. We reconstructed everything, 14 billion years of cosmic evolution, and we have all these wonderful equations, and very smart people like Albert Einstein discovered all that. But in some sense, he only discovered 5%. So what we want to now is understand what the remaining 95% is. And so I hope some of you guys might actually do this. I don't think we will. I don't think we're smart enough. We need new people to come up with ideas. So there are still many kind of big questions. So I'll finish by raising a few big questions that perhaps some of you have. And you can add big questions to it. So let's ask, what do we know about the universe? For instance, how big is the universe? So this is actually, yes, you know the answer? It gets bigger and bigger, that's good. So that's a very good point. So the first point is it's expanding, you're quite right. So I should ask, how big is the universe right now? How big is the piece of the universe that we can see? In fact, that's what you should do. You should look at the visible universe. You see, let's look at the farthest regions of the universe. How far away? Well, you might say, I know the answer. The universe was living for 13.8 billion years. So 13.8 billion light years is the distance. That's not true. Why is it not true? Somebody has an idea? Why is the universe bigger? Yes?
There were no stars until 300 million years or so.
Yeah, so you can add a little bit to it, yes, but there's something else. Huh? No, actually, it has also been expanding. So think about, if you're an ant and you're walking on this balloon, and you go like this, but I'm at the same time blowing up. If you're halfway, and I'm blowing up, actually you speed a little bit further. You go a little bit further. So actually the actual size of the universe, it's just a little fact, is almost like 100 billion light years. From one end to the other. So that's kind of interesting. So you might say, okay, I know how big the universe is, 100 billion light years. So it will take 100 billion years for light to go from one end to the other. But you see, this is the part of the universe we can see. So why can't we see further than that? Who can explain that? Why can't we look further than 100 billion light years? Yes? Yeah, the light hasn't reached us. So the fact that the universe is only 14 billion years old means that we cannot look, because the light takes some time. You see, we think light is going very fast. But already going from the sun to the earth takes 8.5 minutes, which is quite a long time, I feel. No? It's actually, if the sun would explode now, we would have 8.5 minutes. We wouldn't be aware, and then suddenly, it would be pitch dark. But so light actually is going very slow and on the scale of the universe. So we have no idea. So in some sense, it's like you take a lamp and you shine on something, and that's what you see. So this is the part of the universe that we can see. And it's almost like you shine with a light on a wallpaper. You see this pattern. So the question is, would this be the whole universe? Is this, who thinks this is everything? It's kind of obvious that it goes on, right? So is there something outside there? That's a big question. Does the universe continue? No, we call this the cosmic horizon. If you are living on an island and you look around you, you see a part of the Earth. But does the Earth stop at the very end? Will you fall off the Earth? I think that was sometime people thought, it's just a pancake. But would the universe be a pancake? That would be kind of really silly, And actually, we would be right in the middle. We would be in the middle, literally in the middle of the whole universe. So this is kind of, I feel, very unlikely, unless we are very, very special. So probably it continues, but how far will it continue? And it's in some sense, you might think, and you had a good point, the universe expands and expands. But the point is it expands so fast that actually at some point, the region outside our universe is going away from us so fast, it's going actually with the speed of light. So even though it's out there, light can never reach us. So even if you wait 100 billion years, the part of the universe that you can see will not be much bigger. We're roughly at the edge of what we can see. So this is, I find, extremely frustrating. It's being on an island without a boat. So this is our part of the universe. It's out there, probably. We can't see it. We can't. So somebody can ask you, okay, what's happening over there? But we can never see. Nobody will ever communicate. We can never travel there. But probably it's out there. So then suddenly, you feel this is huge universe, but now it suddenly feels very small. It's just a small part that we can see. We are really trapped. There are some other questions. Einstein actually said that the universe could be curved. Like the balloon or something. And it could have all kinds of shapes. And now we can measure it. We can measure very carefully the universe. And you know what? It turns out to be extremely flat. It's not crumpled up at all. It's really like this piece of paper. So this is beautiful theory of curved universe, but the universe is not using it. In fact, it's so flat that with the most precise measurements, we don't see a single curvature. Why? Now, that's another big question. No idea. And okay, so if you look at the universe here, it's closely with it. We have the sun, we have the Earth, we have some nearby galaxies. So it looks like you have all these little dots. But if you zoom out, if you take the big picture, it actually looks very, very uniform. Now, I've shown you these baby pictures of the universe. You think, oh no, when the universe was very small, it was this painting with little dots. But this is like photoshopped. Now, this is actually the universe looked very, very uniform. And the variations there were there on the first page of the book. There were less than 1,000%. So it was like, just try to paint something, where the variations are less than 1,000%. You have to do this extremely careful. So the universe was very flat. It's in some sense, well, large or small, whatever you think about it. But it's finite piece. It's very uniform. And then there's an even more important question, where did it all come from? How did it start? What banged at the Big Bang? And in fact, you can even ask a more deeper question. Why is there something instead of nothing? Why is the universe not empty? Why are we here? It's good questions, right? So the amazing thing is that these are, you might think, oh, okay, why is there something instead of nothing? Why is the universe so big? Why is it, okay, this is nice, it's a nice story, when you're in the campfire. The amazing thing is that right now, at this moment, 18th October 2014, this last point in this big, actually this is the moment where scientists are actually thinking about these questions and they might be close to an answer. So these are the kind of questions that you can find an answer to. And let me tell you perhaps the beginning of the answer. And I want to start with potatoes. So this is a potato. No, and that's in some sense, if you would think, what did Albert Einstein say? He basically said the universe is like a potato. In the sense, it's well, it's kind of ugly. It's curved. It's not perfect sphere. It has a whole lot of bumps to it. Some parts are different than others. It's kind of random. And so in the old days, we thought the universe was like perfect space. You had this flat space. But no, he said, it can be curved. It can be like this balloon or this potato. And then we find out, okay, so the universe is a potato. So let's look at our potato. And it turns out a very special potato. It's very big. It's very flat. It's perfectly the same. How come? Did the universe create this perfect, huge potato, especially for us? No, there's another idea. So what could be going on? Let's see what some of you can think what is happening. Suppose one day you wake up and you see a gigantic potato, perfectly smooth. What has happened? Did somebody grow a huge potato, or something else could have happened? Think about it. What could have happened? Think about some of kind of movies you've seen, where certainly you see huge things. What could have happened? That certainly everything became very large, or what could have happened? Suppose you wake up, not only you see a huge potato, you see a huge banana. Yes? Sorry? Earth could have shrunk. You could have shrunk. Perhaps you shouldn't explain why there's a huge potato. Perhaps you should explain why you are very small. The potato is not very small. You're just, you're like a little bacterium living on this potato. And you look through a microscope at this potato. And of course, when you look through a microscope, suddenly the potato looks very different. Why do people in the old days thought that the Earth was flat? Now we know. By the way, how do we know that the Earth is not flat? Yes?
Because people went out in space and figured it out?
Yeah, that's the perfect answer. Somebody went into space, and they went to the moon, and what did they see?
They saw that the Earth was round.
So they saw, was the Earth very big when they looked from the moon?
No, it was pretty small because the Earth was pretty far away.
They were far away. It's a perfect answer. Very far away. Yes, you? Let me come to that in a moment, yes. But so first we know, how do we know that the Earth is not flat? It's because we can see, at some point people moved from the large distance and on the moon, and they saw a small round Earth. But actually, do you feel it's silly that people think the Earth is flat? If you just kind of, suppose you wake up for the first time, you walk around, Does the Earth look curved? Why not? Doesn't look curved. Because if you think about it, we are really small and the Earth is very big. And if you're on the moon, then the Earth looks small. And you see it's round. But if you're just living, here in town, I'm not kind of moving. If I walk to town, it's not that, it's curved. I have to, it's pretty flat. So one theory is that perhaps the universe is similar. That the part that we see of the universe is a tiny, tiny bit of something much bigger. If that's the case, it's a really silly idea, right? Because if there's anything that's big, it's the universe. It's really big. It's the biggest thing that's there. It's everything. But then say, no, we only see a part. The universe was not around forever. So the part of the universe we see, perhaps we should think of it as a small, small, tiny bit of something much, much, much bigger. Like looking at the microscope at this potato. And it would explain a lot. It would explain why the universe is flat, because clearly everything is flat, like the Earth, if you just look around. It looks very the same, because it's like there's no room for variation. And so that would kind of solve everything. And in fact, that is our latest theory. The latest theory is that the very early universe, which was as big as this ball, wasn't everything. It was created out of a tiny, tiny bit of something bigger. And that's the thing that we call cosmological inflation. I just mentioned this because it's the latest theory. So just after the Big Bang, and you can't even think about it, how short the time was. It was 0.00035 zeros, 1 second after the Big Bang. The universe exploded in a way much bigger than the Big Bang. It exploded it made it a billion times, a billion times, a billion times more bigger. And it created this ball. So this ball that then evolved into the big universe was created out of a little speck that's smaller than the smallest particle. And so our universe would be just a little bit blown up to gigantic proportions. And that would explain a lot. It would explain why the universe is flat. It would explain why the universe has its properties, why it's so uniform. And in fact, it would also explain why there is something instead of nothing. Because, and this is very advanced, so none of you should understand this. But perhaps you know that if you're a small, tiny particle, like an atom or even smaller, you have a different kind of theory that explains it. Some of you perhaps went to the lecture last year, know this. It's the theory of quantum mechanics. And in quantum mechanics, things can just happen randomly. That's the crazy thing of small worlds. And so if this is true, if the universe was created out of this little speck using this cosmic inflation, the small variations that naturally in the quantum world would be blown up to cosmic proportions. So it would explain why there is something. In some sense, these beautiful dots out here would be just the world of elementary particles blown up to cosmic proportion. And I want to end with, so I said, we want to understand the big picture. Now, where are we? And so this is in some sense, I can't make a bigger picture than this. So this is everything we know about the universe. So we know in some sense that there was a beginning, the smallest scales that are there. It's really the scales where space itself would be quantum mechanical, incredibly small. This is the largest distance we know. This is the size of the universe. It's called the Hubble scale. It's this 100 billion light years, 10 to the 25 meters. And if you sit right in the middle, you have the size of a cell, of a bacterium. So if you want to understand the very small distances, you should take the universe, scale it down to the size of a bacterium, and then think of a bacterium inside that miniature universe. You have the smallest distance. So if you go like 1/3, here is the distance to the moon. So, this is the scale of human life. This is where we live. This is as far as human beings have traveled. They traveled not farther than the moon. Of course, our instruments traveled to the very edge of the universe. And here is the size, the smallest size that we have discovered right now. That's the size where elementary particle physics is. Like the Large Atom Smasher, the Large Hadron Collider in Geneva, studies distances like this. So this 3/4 of everything that's out there has been explored. And so this is something that we really want to understand, the smallest things. But the amazing thing that perhaps at the Big Bang, these smallest things were magnified to these cosmic scales. So that would be also kind of very beautiful, because in some sense, to understand the largest structures in the universe, you have to understand the smaller structures. But here I should put a gigantic question mark, because this is just our ideas. These are possible answers to the big questions. So kind of in summarizing, I think it's very impressive that we have these 14-volume sets. So I think you should all read it, all 14 billion pages of it. And again, it was kind of written in less than 100 years, so that's quite an achievement. But I think, we're definitely not done. So there are many volumes have to be added here to understand the universe. And I hope that perhaps some of you write a page in that story. That would be wonderful. So thank you very much. Well, it was a long session, so I think those of you, if you have questions, you can have questions, but we also can have lunch. But are there any questions? Yes.
I don't want. In quantum I
Okay.
in quantum mechanics, like, does it have anything to do with the
I can't understand. So can you use the mic, please?
Does quantum mechanics have anything to do with a debate between free will and determinism?
Free will. Well, there's many things there, but the amazing thing of quantum mechanics is that there is some randomness in it. So if you want to predict what a particle does, you can only say what is the probability that something will happen. So so there is a role of chance. And you might think, well, this is really crazy. Why are these random things there? Why did nature use this? But if this theory about the Big Bang is right, then actually it would tell us that the fact that you are here, the fact that the universe is filled with matter, with galaxies, is because there was this random thing in the beginning. So we all are kind of the result of these random variations, which is, I think, very interesting. And I think so in some sense it would be the answer to why there is something instead of nothing. Now, if there wasn't quantum mechanics, the universe would be just one big soup or something, or nothing interesting would happen. Other questions? Is the question here? No? Oh, yes.
Are there any predictions for what the part of the universe that we can't see is?
Yeah, so what can we know about the part of the universe we can't see? I think, so I guess one thing you could, so in some sense we look at the statistics of our part of the universe. And so it's kind of tempting to think that this will kind of continue, at least. But then, if you go out, I mean, it's like if you're here on the potato, you move a little bit, it's more of the same. But then, of course, the question is what happens if you go out? And now how big is it? And there are fascinating questions. For instance, if you think about how many different things can be happening in this huge universe. And you get interesting philosophical points. For instance, at some point there will be a star that looks very close to our star, the sun. It will have a planet that looks very closely to our planet, the Earth. There will be people perhaps on that planet that look very close to us. In fact, there might be a similar lecture happening at some planet with perhaps a slightly different ending, or it might be exactly the same. So you suddenly realize, wait a moment, there might be kind of clones of me in the other part of the universe. You will never see them. But it will be out there. And if the universe is really big, you can see that, in some sense, there are not that many variations. So you'll have to repeat yourself. Which I think actually, there's another philosophical point which is interesting to know, that you wonder, okay, why am I here? Or why was the whole universe created just for me? Of course, we're all very special, but are we that special? Well, if the universe is much larger, it means that it's kind of doing a lot of variation, and we're just one of them. So that actually puts less of a burden on us to feel very special. But we will still be very special in our part of the universe.
If we switch the analogy of the balloon.
Yes.
So first, if there is a probe satellite around one of the points in the balloon, you can only see as far.
Yes.
Maybe this balloon is only a part of a bigger balloon.
Exactly.
With many balloons
yes.
out.
No, but even, you can say, even if you go, say, one galaxy down the row, and you put an experiment there, you could see a little bit further. Yeah. Of course, it takes us some time to get there, and that's why we get to this cosmic horizon. But in some sense, it would be very silly if literally what we see as the end of the universe is the end. It's just, I think, the end of our observation. But there's no way, by communicating to others, that we kind of extend our range.
But the fact that we extrapolate to the singularity, does that mean that because bigger singularity is just part of bigger?
Yeah. Well, in some sense it is, yes. Yeah. I think we should have lunch. No, there are, I think, probably hamburgers, hot dogs. And whenever you have a question, just come here and we talk further. Thank you for it. Yes.
So there's no imaginable way in which we could communicate, information could pass from?
No.
Absolutely
no.
not.
Absolutely not. Yeah, that's very firm.